This is part one of looking at the VAM differential amplifier design. Firstly, looking at the gain and the bandwidth. Now, the specification for this amplifier says that you need to be within 0.5 dB of the nominal gain over a bandwidth from 40 Hz up to 20 kHz, which is pretty much the whole of the audio frequency range. And we also know that we have this result for the 3 dB bandwidth of a differential amplifier. 3 dB bandwidth is the gain bandwidth product divided by 1 plus the modulus of the gain. Derivation of that is in the lectures or the short introductions. Right, we need an input of 1 millivolt to produce an output of plus 2 dBu. So, what gain do we need? Well, we need to know what a dBu is. And a dBu is a measure of voltage referenced to 0.775 volts. So, if we have plus 2 dBu, that means that plus 2 is 20 log 10 of the voltage in volts, I'll just call it V for now, divided by 0.775. A bit of maths on that produces that V equals 0.775 times 10 to the power of 2 over 20, which is equal to 0.97, call it 0.976, it's close enough, volts. Right. If 1 millivolt input is going to produce that output, that means that our gain has to be 976. Gain, output divided by the input, in this case 976. Okay. If the gain is 976, then what gain bandwidth product do we need for an op-amp to give us that gain with this bandwidth? Well, the spec says that the 3 dB bandwidth is, well, the spec says that the 0.5 dB bandwidth, we can only afford to go down by 0.5 dB in the audio frequency range, so that will be going down by 0.5 dB at 20 kilohertz, and we're just about okay if we can achieve that. What is the relationship between the 0.5 dB bandwidth, which is the frequency range over which you're within 0.5 dBs of the maximum gain, and the 3 dB bandwidth? Well, that comes from a formula that we've seen before. The x dB bandwidth is the 3 dB bandwidth multiplied by the square root of 10 divided by x over 10 minus 1. And using that formula, we can derive the 3 dB bandwidth that we require to get a 0.5 dB bandwidth of 20 kilohertz. Right, that would give us f3 dB is 20 kilohertz. That's our 0.5 dB bandwidth divided by 10 to the power of 0.5 divided by 10 minus 1. And that is 57.3, near enough, kilohertz. So, if we wanted to have dropped by only 0.5 dB by 20 kilohertz, we would be down 3 dB. At 57.3 kilohertz. Okay, so what gain bandwidth product do we need? Well, from the formula on the slide here, we would need a gain bandwidth product of the 3 dB bandwidth we need, 57.3 kilohertz, times 1 plus the modulus of the gain, which here would be 1 plus 976. And that is, as near as makes no difference, 56 megahertz. So, if we were going to produce this amount of gain with an op-amp, we need an op-amp with a gain bandwidth product of 56 megahertz. Have we got an op-amp with a gain bandwidth product of 56 megahertz? Answer, no. The gain bandwidth product of the op-amps that we are using is only 10 megahertz. You can check that on the datasheet. Okay, so does that mean that we cannot produce an amplifier with this amount of gain and this bandwidth using the op-amps that we have available? And the answer is, we can do it. We just can't put all the gain in one stage. We would have to spread the gain out between more than one stage. And in this case, spreading the gain between two stages would work perfectly well. For example, we know we can afford to be 0.5 dB down at 20 kilohertz. So, supposing we had two stages and we were 0.25 dB down at 20 kilohertz in each stage, we would then be 0.5 dB down across both stages. Can we design an amplifier which is 0.25 dB down after just one stage of a two-stage amplifier and still give us this gain of 976 that we need overall? Again, answer yes. If we have an amplifier here with a gain of, say, 32 and an amplifier here with a gain of, say, 31, then overall the gain of these two stages would be 32 times 31, which is 992, near enough. We only have to be within 0.5 dBs of our ideal gain, and 992 would be near enough to the 976 that we're ideally shooting for. The difference in dB would just be 20 log 10, 992 over 976, which is 0.14 dB. That's fine. Means that over most of the frequency ranges, we're actually 0.14 dB above our target of plus 2 dBu. But that just means we can afford to drop a little bit more before we go out of the acceptable range of plus 0.5 to minus 0.5 away from our target. Okay, so we have a gain of 32. What bandwidth would we get out of it? Well, assuming this first stage is a differential input stage, the 3 dB bandwidth that we would get would be the gain bandwidth product, which is 10 megahertz for the op-amps that we have available, divided by 1 plus 32, which is 10 megahertz divided by 33, which is about 300 kilohertz. And if our 3 dB bandwidth is 300 kilohertz, then our 0.25 dB bandwidth would be 300 kilohertz, our 3 dB bandwidth, times the square root of 10 to the power of 0.25 over 10 minus 1. That's the formula we've used before. That would give us 300,000 times the square root of 10 to the power of 0.025 minus 1. Answer, about 73 kilohertz. 73 kilohertz is well above the 20 kilohertz that's our design target, so yes, this is going to work absolutely fine. Two stages, both with gains of around about 31 or 32, will give us the gain that we need, and they will give us the bandwidth that we need as well. So that's what we'll do. We'll split the gain between two stages. How you choose to split the gain between the two stages is up to you. To maximize the bandwidth, you ideally want about the same gain in both stages. But to maximize the noise performance, so you minimize the total noise in the output, you'd want as much gain as possible in the first stage. Another consideration is that it's slightly easier to give a reliable and constant input impedance if you put more of the gain in the second stage. So there's swings and roundabouts here. But putting about the same gain in both of the stages, or maybe slightly more in the first stage to give you slightly better noise performance, would be a sensible choice.